Hello, welcome to video 2 for section 4.3, talking about bases for null space and column space of A. That's right, in the previous section we found, not the previous video, but the previous section, we found a spanning set for null A and observed that it was also linearly independent. As we now know, that means that the spanning set we found is actually a basis of the null space of A. So we can punch to the previous section and say the technique for finding a spanning set for the null spaces actually finds a basis too. So we're all set there. It remains to figure out how to find a basis for the column space of A. So let's examine the very simplest case. This is when we're looking for the column space of a matrix B, let's say, that's already in echelon form. So we'll just name each of the column vectors B1, B2 up through B5. And we know that B1, B3, and B5 are our pivot columns. And we can check that B2 is just 3 times B1, and B4 is just 4B1 plus 2B2, or 2B3. So we have these relationships among the columns. By our spanning theorem? Spanning set theorem, I guess, is really what it's called. Let me add the notes here. Spanning set theorem. By the theorem we saw last video, we know that the span of the columns of our matrix B, actually all we need are the ones that aren't linear combinations of the others. So certainly the span of B1 through B5 is equal to the span of B1, 3, and 5. And then if you look at 1, 3, and 5 really carefully, these are some of the columns of the identity matrix. And so we know they're linearly independent. And so we get automatically that B1 through B5 or B1, B3, B5 are linearly independent, and they have to span all of the column space because the column space is just the span of these 5 columns, and we just saw that it's equal to the span of B1, B3, B5. So we've successfully found a basis for our column space, namely the span of the pivot columns. And so a natural question once we've sorted out this easiest case is, well, what happens if our matrix A is not in echelon form? And then of course what we should do is reduce to echelon form. I've saved us the onerous work of doing that. I'll let you check this if you're so inclined. Check. It's obviously not a single move here. There's many moves, but they are equivalent. They are row equivalent. And then the observation is that since B2 is 3 times B1 over here, we know this is the little clever observation that we need to make. Since B2 is 3B1, we know that A2 is also going to be 3A1. And similarly, A4 is going to be 4A1 plus 2A3. And this one at least is easy to check. The other one happens to be true, and the reason it's true is because row operations preserve these sort of linear relationships among columns. Right, so it's easier to check that A2 really is 3 times A1. Harder to check this, but not very hard. Just a little bit of arithmetic for you. The point is, this means that the span of A1 through A5, this is the entire column space, is equal to the span of A1, 3, and 5. And since A1, 3, and 5 again are since B1, B3, B5 are linearly independent, so are A1, A3, A5. And so we get that A1, 3, 5 forms a basis for our column space. And the little note here, it's easy to get confused. The basis of the column space of A is going to be made out of pivot columns of A. So in practice, we take our matrix, reduce it to echelon form, find the pivot columns, and then select the corresponding columns from our original matrix. And that forms the basis of the column space of A. It is not true that the columns of the echelon form make a basis for the column space of A. And so we've proven this little theorem more or less. The pivot columns of A, pivot columns of A form a basis for the column space of A. Okay. It was a nice little quick one. I'll see you all next time for 4.4. Take care, everybody.